Hello, hello, and welcome back to Introduction to Algorithms. Today, we're going to have a recap of the last part of Chapter 3, Sorting Algorithms Beyond the Comparison-Based Paradigm. And then we're going to have a recap of the entire first 3 chapters, because these 3 chapters are relevant for the midterm exam that is coming up. So you already see here the slide, and the distinction that I want to emphasize here is between comparison-based and non-comparison-based algorithms. A comparison-based sorting algorithm is one that uses only 2 primitives, namely comparing 2 elements from the input array and swapping 2 elements from the input array. And this is one of the examples where our virtue of computer science comes in so handy and helpful. Namely, we agreed that we will always indicate which operations the algorithms we're developing, which primitive operations these algorithms use. And indeed here, bubble sort, merge sort, insertion sort, quick sort, all these algorithms use only these 2 operations, comparing 2 elements from the input array and swapping 2 elements from the input array. And this is what makes them comparison-based sorting algorithms. And for comparison-based sorting algorithms, we were able to prove a particularly powerful theorem, namely a statement that any comparison-based sorting algorithm requires at least n log n steps in order to sort n elements. And this is so powerful and mathematical a statement because it pertains to any comparison-based sorting algorithm, even the ones that people may and will devise later. So there's an entire research area about developing new comparison-based sorting algorithms, and all of them, according to the theorem, require at least n log n steps in order to sort. And we were able to prove that theorem by combining these 3 items from the above lemma, which I'm not going to repeat. But this mathematical statement, the theorem, also provides an interesting approach in order to devise more efficient algorithms, namely in order to get closer to linear time algorithms, sorting algorithms, we have to resort to non-comparison based. We need to look at algorithms that use primitives other than just comparison and, still swapping, but not just comparison. And indeed, we have devised 2 such algorithms, one for sorting integers from a certain range, 1 to capital M, and another algorithm for sorting binary strings of length small m. And actually, the performance of these 2 algorithms depends on the range of integers, capital M, and on the length of the binary strings, small m. And also, naturally, these 2 algorithms make use of the special kind of data that we're operating in order to use new primitives beyond just comparison. For example, when sorting integers in the range from 1 to m, our algorithm made use of the fact that such integers can serve as indices into an array, which is not the case for generic data. And our algorithm for sorting binary strings of length m made use of the fact that one can access individual bits in this binary string, which again is not the case for generic data. Both these operations leave the realm of just comparison based. So let's recall our algorithm for sorting integers from the range of 1 to m. And that algorithm, in addition to the input integer array, uses a helper array, very similar to our first hashing-based algorithm, with the disadvantage that this helper array may occupy a large amount of memory, namely as much memory as the range of integers, m entries. So this is our helper array, and hopefully this helper array is smaller than the input array, meaning that the range of integers we're sorting is smaller than the number of items. This hypothesis, this expectation also means that many elements will occur repeatedly. So this is where counting sort becomes efficient, when we have integers from many integers from a small range, and therefore integers occurring repeatedly. And in this case, the algorithm will first initialize this helper array and then increase and count in each entry how often that element occurs, how often entry 1 occurs, how often entry 2 occurs, and how often entry m occurs. Because, recall our hypothesis, we're only dealing with integers in the range from 1 to m. So all integers will be in some of these ranges. And this loop counts how often each integer occurs. And once we know how often each integer occurs, we can easily calculate where these integers will end up in the sorted array after sorting. Namely, the integers in this example, 1 occurs 3 times, meaning that the first 3 elements in the output sorted array will all be repeatedly this element. Then the next 2 entries go here, the next 4 entries go here, and so on. So by adding all these numbers, we can calculate where these entries will end up. And this is exactly what the next loop does, namely adding all these entries up. And after these calculations, here you see, the entries in the helper array indicate where the original input entries will end up after sorting. And this is what the final loop does. And the final loop proceeds from bottom down to prevent overwriting elements. Right. So the correctness of this algorithm is thus pretty obvious, right? And the running time analysis is also obvious. We have no nested loops. We have 2 loops ranging from 1 to m and 2 loops ranging from 1 to n. So the overall running time is n plus m. And as I promised, the size of the range of integers that we're sorting, capital M, enters into the efficiency, affects the efficiency. It also affects the memory use. And final observation, this is not a comparison-based algorithm, right? It uses other primitives beyond just comparison, namely it uses the data entries, the integers, as indices to the helper array, which is not one of the comparison-based primitives. And in this way, the algorithm is able to beat the n log n lower bound and get down to linear time, only O of n plus m. Yes. Let's, this is the first analysis of the counting sort, counting the number of operations. But as you recall, this may give an inaccurate, unrealistic prediction of the actual performance of the algorithm. We may want to look more closely at the number of bit operations incurred by these algorithms. So let's now look at the number of bit operations by counting how many bits does each entry here have. So we have here integers in the range from 1 to m. That means we have log m bits in each of these operations. So that in the bit model, the running time of this algorithm is actually um, n plus m log m. So we need to multiply every operation with a factor log n and log m to reflect that the integers in the range from 1 to n have log n bits, and the integers in the range from 1 to m have log m bits. I'll get back to that when we recall and compare all these algorithms. And yeah, big disadvantage maybe is that, like with our initial hashing, the memory consumption of the algorithm also depends on the size of integers that we're operating on. So that's also n plus m. That's our first non-comparison based linear time sorting algorithm, counting sort resorting integers. And now we are going to recall our second non-comparison based sorting algorithm, this time for sorting binary strings of length small m. Now this is so-called Radix sort, and here we consider the binary strings equipped with a lexicographical order, which is a total order. Lexicographical order means that the first bit determines whether two strings are smaller or larger if the first bits disagree. If the first bit agrees, then we look at the next bit to see which of the two strings is larger or smaller with respect to lexicographical order. And this is exactly what is also known as dictionary order for in the old days when phone dictionaries were sorted to facilitate finding people's phone numbers in the dictionary book. So here's a definition of the lexicographical order. If the first bits disagree, then that determines that the string starting with 0 is smaller than the string starting with 1. If the first bits agree, then look at the next bit to see which of the string is smaller or larger, and so on. And Radix sort is another linear time sorting algorithm, non-comparison based, which uses the non-comparison based primitive of looking at individual bits in this special kind of data bit strings. So this is a kind of recursive algorithm. It looks like a recursive algorithm, but it can easily be unrolled. I'll get back to that when we analyze the performance of the algorithm. And the algorithm first looks at the most significant, the leading bit, because that determines has the priority in lexicographical order, and it uses this split operation that we also had seen before when considering the linear time median and we're considering quicksort. Namely, it puts all entries, all bit strings that start with 0 in front of all those that start with 1. Okay, so this is the split operation, and split operation operates in place. It uses the existing array, and as a result of the split operation, it will tell how many bits had entry 0 and how many had started with entry 1. That's the result here. And then recursively, the algorithm will sort those that start with 0 only, and it will separately sort those that start with bit 1, again, individually without considering the others. And there's the first ones are those that range up to index mid, and the last one are those that start with index mid plus 1 according to this return value. And observe that this is not really, I mean, this looks like two recursive calls, but basically the overall cost of the two recursive calls is simply the same size of the array again, right? This is up to position mid, this is up to position mid plus 1. And now in the next level, the algorithm will look at the next significant bit. Here it looked at the most significant bit, the one at position M, right? That's the most initial one. Then at the one at position M minus 1, then the one at position M minus 2, and so on. So that this basically means we have M loops, right? No, one loop of M iterations looking at each bit, and in each loop, N elements are being sorted. Here, elements up to position mid, and here from position mid plus 1 up to capital N, so that the overall running time of this algorithm is N times M operations. And again, observe that this is not a comparison-based algorithm because it really looks at individual bits rather than just comparing entire strings. An algorithm that would only compare entire strings, that would be a comparison-based algorithm, but this algorithm looks at individual bits. And similar to the previous refined analysis of counting sort, now we're going to reanalyze Radix sort from the more refined perspective of bit cost. And the bit cost analysis here is also very simple, namely only observe that every operation we use on string is actually M operations on M bits. So multiplying the original unit cost analysis, counting the number of operation, each operation incurs bit cost small m, so multiplying everything with small m, that gives this bit cost n times m squared. So that's our second non-comparison based algorithm, or second algorithm. And here's a great question in the chat. Namely, since the algorithm makes two recursive calls, and we had several algorithms before making two recursive calls, and the algorithms we discussed before making two recursive calls, such as quicksort, resulting in a running time n log n, right? Now the question here is, why is this not n log n, but n times m? And if you look closely, n times m is actually n log n in disguise. Let me recall that if we have bit strings of length m, then that means we can have at most 2 to the m different bit strings, right? So that means if the bit strings are distinct, different, then n is at most 2 to the m, and conversely, m is at most the logarithm of n. So in a sense, this is still an n log n algorithm, but with a refined analysis, if many bit strings are repeated, if m is much smaller than log n, then this algorithm kind of allows to beat the n log n. But if we have long bit strings, then this gets worse than n log n. So this is a great question because also it starts our question about comparing the different sorting algorithms. So which one should one use, right? So suppose you are asked to sort bit strings, then you could either use quicksort to do so, or you could use Radix sort. Which one would you want to do? And the answer is it depends on the length of the bit strings. If the bit strings length of the bit strings is less than log n, then Radix sort is better. And if the length of the bit strings is greater than log n, then actually quicksort may be better. When counting the number of operations, when counting the number of bits, then this algorithm is always better. Thank you for this excellent question. So to move on, these are two examples of non-comparison band algorithms, algorithms that superficially seem to beat the n log n lower bound, but on closer inspection, there's still something like n log n present in some cases, depending on the input parameters, the relation between n, the number of elements, and m, the length of the bit strings to be sorted. So that, yeah, for comparison, for reference, here's the statement of the bit cost of quick and merge sort, our optimal n log n algorithms counting the number of operations. But now when we want to sort bit strings, each operation amounts to m bit operations, so multiplying the overall cost with m results in the overall bit cost. And now you see when m is smaller than log n, then this is better. And when m is larger than log n, then actually quick or merge sort are preferable. Good. Right, and the final topic in our chapter 3 was about sorting in parallel, namely a special kind of parallel sorting algorithms called sorting networks. Sorting networks are kind of, again, following our virtue of stating which primitives we're going to use, and sorting networks are parallel algorithms that use only one sorting primitive, named a so-called gate. And the gate is kind of like, yeah, if you recall Boolean circuits, you know gates, AND gate, OR gate, negation gate. And here we have a sorting primitive that compares two elements and swaps the two elements if they're in the wrong order. So here we don't have two separate primitives, comparison and sort and swapping, but only one primitive, compare and swap if in the wrong order automatically. And you see the semantics here. This is one sorting primitive. In this example, the input elements are already in sorted order. 1 is less than 3. The same gate, when presented with input in wrong order, will swap them so that after every swapping gate, at the end, the two elements that have been fed into the gate are always in correct order, but only two elements. And now let's combine these sorting gates to sort more than just two elements, to sort up to n elements. And here you see a combination of these sorting gates that sort 4 elements, right? First compare these two elements, then compare these two elements, then compare these two elements, and compare these two elements, and then compare these two elements. So that means this is a parallel algorithm using a total of 5 sorting primitive gates in order to sort 4 elements. I would like to ask you to convince yourself that this really sorts, that at the end, the input array has been sorted. At the end, whatever the input entries are in the at the end, they are going to be sorted. Here you see an example, kind of an example run of this sorting network with 5 gates, sorting the input 1, 4, 2, 3. So first, compare 3 to 4. That's already in the right order. Then compare 2 to 1. That's in the wrong order, so it gets swapped, right? 1 moves up here and 2 moves down here. So now 1 and 2 are in correct sort order. Then these two elements are being compared. They're in wrong order and thus they are swapped. These two elements are being compared. They're in the wrong order, and thus they're being swapped. And finally, these two elements are compared, again in the wrong order, so they're being swapped. And at the end, all elements have been put into the right order, they have been sorted. And this is just one example, one input permutation of 4 elements. And please convince yourself that indeed every possible input permutation at the end results in being sorted. So that this is an example of what is called a sorting network. And why is this a way of sorting parallel? Because some of these operations can be carried out concurrently. Now, for example, these two elements are being compared and possibly swapped or not. And these two are being compared and possibly swapped or not. But they can be compared and possibly swapped independently of each other because they don't, the output of one doesn't affect the input of the other. So these two comparisons can be executed simultaneously in parallel. Same here. Here it's even more visually striking. These two are being compared. These two are being compared, and they don't affect each other, so they can be conducted simultaneously. But this one must only be conducted after this one has ended, because here you see they both access the same data, right? Similar here, this one can only be executed after this one has ended, finished, because it uses the same data. And also this one can be compared only after these two have finished, because it uses the output from the previous comparison. So that this sorting algorithm only uses 3 time steps in parallel. These two together in one time step, these two together in one time step, and this pile 1 in one time step. 3 time steps to sort 4 elements using 5 gates. More generally, here's an example of a sorting network for sorting n elements for arbitrary n. And if you look at it, this is basically turning bubble sort into a sorting network, right? So here you see the first 2 elements being compared. If they're wrong, they're swapped. Next elements are compared. If they're wrong, they're being swapped, and so on until down here. That's the first outer loop of bubble sort. Then the next execution of the iteration of the outer loop, again with an inner loop, now ranging only up to here. This is another execution of the outer loop with the inner loop only ranging up to here, and so on. So that kind of basically unrolling, one can unroll any possible comparison-based sorting algorithm into a sorting network. And here we have unrolled bubble sort into a sorting network. And now let's analyze this sorting network. And with any parallel algorithm, you use 2 ways of analyzing. First is the number of gates used. And the number of gates is the same as the number of gates comparison used in bubble sort, namely n squared gates. And here you see n minus 1 gates. Here you see n minus 2, n minus 3, n minus 4, and so on. And adding these all up results in n squared gates. That's what is called the size of the sorting network. How many gates does it use? And the other interesting thing about analyzing sorting networks is the running time they use, because now we really have the ability to run things in parallel, and thus the parallel running time is actually smaller than the sequential running time of bubble sort. Let me say it again. Turning bubble sort into a sorting network allows us to execute certain operations in parallel, and we see which operations can be executed in parallel, which is not so apparent in bubble sort. If you parallelize bubble sort, this is maybe one way of finding efficient ways of parallelizing bubble sort. First, turning it into a sorting network, and then see, for example, that after these 2 comparison operations have been finished, and this one is starting, we can start this comparison concurrently to this one. These two can be executed in parallel. And these two can be executed in parallel because they operate on disjoint data. These two can be operated in parallel because they operate on disjoint data. And same here, this one can start operating once this one has finished, can operate currently to this one. This can operate currently to this one, and so on. So all these concurrent, some of the gates can operate in parallel if they operate on disjoint data. If they operate on same data, then one primitive must first finish before the next one can start. And now let's look how many kind of phases of independent parallel execution this so-called bubble sorting network uses. Well, it's kind of these two, that's a constant number. And then once these start, we can start with the next phase, this one. So if you continue this analysis, you will see that this bubble sorting network, I already said, has quadratic size, a quadratic number of gates, like bubble sort's sequential running time, but the parallel running time of this sorting network is only linear, so it's actually faster. But it of course it operates in parallel. Yeah, so this is a great example of how parallel computing actually can accelerate algorithms. Namely here, this is a comparison-based parallel sorting network using less than n log n running time, namely only O of n linear running time for sorting. But of course, the overall so-called work done by this is the size is still quadratic, so it's worse than, for example, merge sort or quick sort. And this raises the question of optimality, right? Remember our virtues, optimality. What is an optimal parallel sorting algorithm? What is an optimal parallel sorting network? And it is not too hard to see that any sorting network must have parallel runtime at least log n and must have size at least O of n. And the famous theorem in computer science says that such sorting networks actually exist. It says there exist sorting networks of size n log n gates, and depth log n. So very fast logarithmic running time, as you recall, is very fast. Yes, so sorting in parallel is becomes very efficient, and the proof of this theorem is very involved. It seems very hard to construct such sorting networks in a sense explicitly. But I want to refer you to an advanced lecture on parallel algorithms that will provide maybe a proof, and that will also discuss other parallel algorithms for other problems, and optimality of parallel algorithms is also a very famous research topic. So that concludes our recap of chapter 3 on sorting. We talked about specification of sorting, talked about first comparison-based sorting algorithms, bubble, selection, insertion, merge, and quicksort. In quicksort, we realized that quicksort is not really quick unless we put some effort into the choice of pivot. And the choice we made here is using the linear time median algorithm that we discussed in chapter 2. And we were able to prove that any comparison-based sorting algorithm requires n log n running time. Thus, quicksort and merge sort are both optimal in terms of running time. quick sort also in terms of memory, merge sort not in terms of memory. And this raises the question about non-comparison based sorting algorithm. And here we discuss two algorithms for sorting in what superficially seems like linear time, namely sorting integers, but here the range of integers affects the running time, and sorting binary strings in linear time, but here the length of the binary strings enters into the running time. And finally, we discussed sorting in parallel. So yeah, that concludes our recap of the last part of chapter 3, sorting. And now we're going to take a short break here. And this is an opportunity for you to ask questions in the chat that I will then answer. Thank you for now, but we will resume after a short break with your questions. So please write your question. Here we're back. Thank you very much for your questions in the chat. And one very interesting question, thank you very much, is about the bit cost of counting sort. Yes, indeed, we have analyzed algorithms usually in the so-called unit cost measure, counting the number of operations, but ignoring how large the data is being processed in each operation, how many bits each operation operates on. By counting, that means charging just one operation for each operation, regardless of the number of bits used for each operation. Whereas a more refined analysis also takes into account the number of bits used and operated on in each operation. And let's do that also for counting sort explicitly. So here you see our runtime analysis and our memory use of counting sort in the unit cost, only counting the number of operations and only counting the number of array items. But of course, each array item also has a certain bit length. And what you see here now is the bit cost of counting sort. And basically, the bit cost comes from multiplying each operation with the length of the number of bits used in the operation. And so, for example, if the integers range from 1 to m, then that means we have log m bits for each integer. So each operation is multiplied with log m. And similarly, when we talk about integers in the range from 1 to n, then each such integer has log n bits, and we need to multiply everything with log n. So this is a bit cost analysis of counting sort, and we already did similar bit cost analysis of Radix sort, here multiplying every operation with m, because we're talking about bit strings of length m, so every operation incurs m bit operations. And we also similarly analyzed the bit cost of our previously optimal algorithm, quick and merge sort, multiplying everything with m, that is basically with the number of bit, the bit length of the bit strings. So that answers a very good question about the bit cost analysis. And another question was about the content of the midterm. And yes, just a second for the midterm. The midterm will cover the first 3 chapters. So we already recalled chapter 3 on sorting. Then moving back, chapter 2 is about searching. In chapter 2, we emphasized and applied our virtues of computer science, specification, primitives with semantics and cost, design and analysis of algorithms, and proof of optimality for searching problems, linear search, neighbor search, binary search, uniqueness problem, hashing-based algorithms, and median, as well as the generalization or the statistics calculation in the linear time. And we concluded chapter 2 in searching with geometric search problems, namely range counting in dimension 1, 2, and higher, counting, range counting, and range reporting. That is our recap of chapter 2. And initially, we started with chapter 1, introduction, about computational problems and their algorithmic solutions, where we illustrated and emphasized the power of abstraction, your computer based on quantum mechanical principles, but you don't need to know quantum mechanics in order to write programs. And that's several layers of abstraction from quantum mechanics via transistors, via integrated circuits, CPUs, and so on to a high-level programming language. We talked about the virtues of computer science from problem specification via algorithm design as opposed to coding and algorithmic analysis, correctness, and asymptotic cost, to the question of optimality with the example of a abstract powering problem and the square and multiply algorithm for solving abstract powering. Then we emphasized the importance of which primitive operations and what cost to charge the primitive operations by considering 4 different algorithms computing Fibonacci numbers, more and more efficient from exponential time via polynomial time, via linear time, up to logarithmic time and constant time even, but at the same time using more and more powerful primitives from only incrementing and addition to also using multiplication, and finally even exponentiation and logarithm of irrational number. Then we use the master theorem in order to analyze the asymptotic cost of several algorithms for polynomial multiplication, long multiplication, Karat-Zuba multiplication, Thom multiplication, and the entire family of multiplication algorithms due to Stephen Cook. So that was the content of this course so far, first 3 chapters, and this is also what the midterm exam will cover. And regarding administrative details for the midterm, please refer to the TAs who take care of that. So for today, that's all. Thank you very much for your attention, and see you on Thursday for the final lecture before the midterm exam.